be great. Great. So good morning, everyone. Thanks for joining us for another NL seminar. Today, it's my absolute pleasure to introduce Zhou Yao. Zhou has joined the CS department at Columbia University in January 2021 as an assistant professor. Before that, she was an assistant professor at UC Davis. She obtained her PhD from Carnegie Mellon University in 2017. Zhou has built various dialogue systems that have a real impact, such as a job interview training system, a depression screening system, and the second language learning system. Her research interest includes dialogue system, language understanding and generation, vision and language, human-computer interaction, and social robots. Zhou received an ACL 2019 Best Paper nomination, was featured in Forbes 2018 30 Under 30 in Science, and won the 2018 Amazon Alexa Prize. So thank you so much, Zhou, for accepting our invitation. And with that, I leave it to you. Everyone, please join me in welcoming Zhou and enjoying her talk. Thank you.
Thanks for inviting me. Let me share my screen. Hi everyone, I'm Zhou from Columbia. So I'd like to take questions in between as well. So I'll pause in between some of the two sections to get more questions, and we'll also take questions in the end. So today I'm talking about teaching machines effectively through natural language and a conversation. So before I go on, I wanted to just briefly introduce my lab and about directions we do. We mostly focus on dialogues, but the real ideal is to enable natural communication between humans and machines. And this is complex enough that we actually require more than NLP skills. So we're talking about natural language understanding the intent of the user. This is also coming from different languages. It could from ASR outputs or comparing to typing outputs. We're also looking at, once we understand the human, we're on to understand how do we plan the actions of the system or robots in order to achieve the goal better. So we're talking about supervised learning, imitation learning, and reinforcement learning in terms of planning. Once the robot knows what it needs to do, it also needs to generate natural language that can be understood by a human easily. So here we're talking about various techniques such as conditional generation, any particular pragmatics or semantics you want to inject in the generation process. And we're also talking about consistencies over conversations, adaptations to individual users that could all be done in this language generation section. And finally, we say in natural communication, we're not constraining ourselves in terms of language. Not only typing language, but audio, but also we can see people. So vision, acoustic, touch, all these are important factors people take into consideration in order to achieve tasks better communication, better rapport. So we wanted to enable machine to have the access to all these channels of information and how to blend them together, how to utilize them together for better understanding the human, the situation in order to coordinate with the human better. Finally, we know there are a lot of meanings are between sentences. How do we infuse common sense that is in between the lines? We're not only talking about simple common sense, such as Wikipedia or ConceptNet. We're even talking about broader aspects of cultural difference and so on. How can we represent them and infuse them with the robot in order to have a more natural conversation? Finally, in my lab, I also work on, if we are working on conversational system, we know there is a huge gap between training and testing, because we're training on human-human conversations. While doing the testing, people know it's a chatbot, right? So would that actually have a huge sort of discrepancy between the models you train for human-human? So it really comes down into looking at human-computer interaction. How can we position the robot in order to not cause all these kind of uncanny valley issues in order to have natural effective communication? How can we be transparent? How can we not mislead human? How can we guarantee safety? So my lab has been working on all these perspectives. If you wanted to look at individual papers, please free to just go to my website and you'll see all these papers with citations and codes and data. So today, we're mostly going to not talk too much about dialogues, but talk about general machine learning problems. So as we know, nowadays, neural network-based models are everywhere. And it's creating a huge phenomenon of successful downstream tasks. However, it requires a lot of numerous annotated data in order to train a good supervised classifiers. So usually the current paradigm usually have 3 steps. You collect data. It could be images or text or whatever. And then you label them. You invite humans to label them. And then finally, given the labels, you train a model. So the 3 steps currently are very separated from each other. So you do one and you do the next. But in reality, they should all be integrated together because of human involvement. So for example, each individual data is not sharing or contributing equally to the model. And each labeled data is not contributing to the model equally. We should collect data that is useful, complementary to each other, and we should label the data the same way. So can we actually look into how do we combine learning methods and the human interaction, because humans have to collect the data. Humans have to label the data in a smart, efficient way to have a more integral learning process. So we know instance-based active learning has been there for a long time, and which has a very simple and clear idea. For example, we're looking at a 2-class classification. We're looking for a decision boundaries to classify the red from the green. So obviously the points, the data points that are closer to the decision boundaries would contribute much more information than the data points that are far away. So active learning is really saying we shouldn't label every single data point that we collected. We should only label the ones that are contributing for mostly basically resolving the uncertainty of the learning model. And this has been sort of studied for a couple of decades now. But in reality, is this sort of instance-based active learning enough? Not really. So we wanted to see if there is a better way to communicate with humans other than simply asking people to label data. As we know, if you're doing a classification problem, then if you ask people to label if this is a cat or if it's a dog, so the information gain is really minimal. And so 1/2 vectors in terms of like you get like 1 bit of information. However, humans are much better than telling you it's a dog or a cat. It can give you natural language explanations. People are good with language because they're born and sort of accustomed to interact with anything through natural language. And natural language has much more complex syntax. It can express a lot of abstract meanings, could help your classifiers, but it also imposes difficulties in understanding them correctly. So today we're just going to talk about how do we utilize natural language explanations in a smart way to improve performances of low resource classification tasks. So first we're going to test everybody for a simple question. So we want to do this famous bird species classification. There is this particular bird called a ring-billed gull, and this is on the left, top left. So you can see it everywhere in California. We wanted to ask you if you have ABC3 pictures. 2 of them are ring-billed gulls, and 1 of them is a California gull. Which one is a California gull? Any guesses? Okay, we have a C, and we have an A. Okay, it's half-half. Okay. It's not C. Rainbow Gull changed their coat color from yellow to gray after the first winter. So color is not the deciding factor to distinguish California gull and rainbow gull. The key is really about the ring. So rainbow gull has a bill with a black ring near the tip, where California gull has a red spot near the tip of the lower mandible. So now it's very clear that we have the sky on the top right, which is actually had this red spot instead of the black ring. So that's the California gull. So we had many people got it right. So if we have a contrastive natural language explanation, such as rainbow gull has a bill with a black ring near the tip, while California gull has a red spot near the tip of lower mandible. So if we can parse this information and tell it to the classifier, we can do this much better. So here I particularly want to point it out. For these particular classification problems, which experts are really hard to get, are extremely beneficial to have these kind of natural language in help of labeling. So we can think about similar tasks such as medical imaging classifications and so on. Because these tasks, you can't just simply target, because normal people do not understand or cannot give you particular annotations. So our method is simply we want to propose this kind of active learning with contrastive natural language explanations. And here we're particularly using class-based active learning. So we're actively selecting classes to differentiate instead of particular instances. So here we have, we want to differentiate, for example, rainbow gull and California gull. This is just one particular example occurring. So if you have a C number of classes, you can have a C squared number of possible class pairs. Of course, you don't want it to random sample them. You want it to sample two classes that are like most confusing to you. So we're gonna bootstrap starts from a small label training set, interact with human experts for K rounds. For each round, we'll ask B number of explanations in order to infuse our classifier with more information. So I just want to clarify, instance-based active learning is really you ask the human to give you a particular label for a particular instance. While class-based active learning, you wanted to, we wanted to ask human to give us an explanation between that can differentiate the two classes. So there are 3 steps in our framework. First of all, we're going to define how to select the classes. And then second, how do we parse the natural language explanation and ground that back to the data? Finally, how do we change the machine learning model in order to incorporate the information we got from natural language? First, suppose we have this data set. We only have very few number of examples for each classes. So we have this rainbow gull, California gull, we have this kind of a human gull, other Arctic tern, least tern. And then what we want to do is using multivariate Gaussian to fit each classes. We fit them into a feature space. And then we want to select B number of pairs of classes that has the lowest Jensen-Shannon divergence distance, which means they are closest together in this particular space. Of course, you can use other generative models to figure out which 2 classes are closer. This is just one example of way to approximate it. So, for example, here we find the most confusing 2 pairs are rainbow gull versus California gull, and then we're going to select it. So, so here particularly, we're going to greatly select different pairs. You can also try to use certain ways to optimize the selection as well from a global planning perspective. Then the second step is we're going to generate a natural language question based on a template, saying how to differentiate Rainbow Go and California Go. And then the expert will receive the query, and we ask him to tell us, we will give them a template and ask them to respond in a specific way. For example, the biggest difference between Rainbow Go and California Go is, and then he can fill the rest of it. For example, he said, Rainbow Go has a bill with a black ring at the tip, blah, blah, blah. And then we're gonna parse that particular sentence and extract information that is important to us. Here in particular, we're extracting the noun phrases, Rainbow Go, California Go, and then the bill, which is the part that we, that differentiate, the body part that differentiates the two species. And then once we detect it, it's the language, it's a particular word bill that is gonna pay the most important difference. What we're going to do later is we're going to map this particular language bill into a visual patch. So we have particular, so this data set has some previous data that we are that could build with annotations of different bird parts. So we can pre-build these kind of bird parts detector. And then for each images, we can detect the bill portion of the picture. And so that's why how we connect the bill and the patch together. Finally, the third part is once we know where the patch is, the next thing is how do we incorporate that? How do we put more emphasis on that particular patch? So there are different ways you can do it. Here, we're just giving you an example of how we did it. So as we know, for example, we have 15 species, and then it's a 15 class classification problem. So if you think of the image encoder, you go into the classifier, you have like 15 classes on your right. But now we're gonna morph it, making it a hierarchical, which means we're gonna combine Rainbow Go and California Go into a supernode, which is California Go or Rainbow Go. And then we're gonna have a further second layer to further classify Rainbow Go and California Go based on the local classifier, which is the patch that we grounded on, which is the bill. Of course, these patches could come in different conditions. For example, if there is some other things, other species, the important part is not just the bill, it's a leg, or it's a feather. Then we have different type of local classifiers. So how do we collect these explanations? So we mostly talk about the contrastive explanation, the difference between contrastive explanations and generative explanations. Contrastive explanations is really asking people to tell the most distinguishable features between A and B, while generative descriptions are usually more holistic. It's usually good for like a generative model, but not particularly suitable for a discriminative model. Because sometimes if you describe holistic information, it's not detailed enough to for differentiating with a different species. So usually we find human also learn better through contrastive explanation. So here particularly, that's a major reason that we adopted the contrastive explanations in our work. Now we're ready to set up the experiments. We have this CUB data bird species classification data set. So we randomly sample 25 classes. For each class, we want to give it 15 images per bird species with labels. So there is only 15 data points, which is very little. And then we ask experts 4 rounds. And for each round, we select 3 classes, and we ask them contrastive explanations in between classes. So you have basically class 1 versus class 2, classes 1 versus class 3, classes 2 versus class 3. And then you do 4 rounds that way, so you get it to select a couple times. And then we're gonna compare with different type of baselines. First, we're looking at if we don't do the grounding, which means that we don't particularly select a certain patch, we're not doing that good. While if we don't morph the hierarchy, it's not that helpful. If we randomly pick a patch, it's not really good. If we randomly pick a pair, it's also not good. So we can see for each round, of course, Alice is doing much better. And then once Alice, after 4 rounds, can close to 91% for subfamily and 76 for the species. So another important factor that we want to consider is the instance. The other parts I also wanted to say here is 6, 7, 8 columns. These are random sampling plus the 33% of extra data. So for example, previously we have 15, so we basically are adding 5 more data points inside of it. And we're randomly sampling images to label. And it's not doing that much better. And even like increasing 100% data, it's just very close to what Alice has. We also compared it with instance-based active learning. Of course, we wanted to see, is this kind of class-based explanation going to help us more? We do find all these kind of instant-based class, if we add like 33%, 66%, it's not that good compared to Alice. Another thing that we wanted to look at is, of course, how many, so one explanation equals how many labeled sample. So we plotted on the right, for example, we have 3 explanations, and it's close to 65 additional, 125 additional data points. So if you look at a ballpark of these graphs, one explanation roughly equals 30 labeled data. So you can roughly ask people an explanation and then ask them to label 30 data and try to time it to see which one is quicker. But usually we do find one explanation is much faster compared to annotating 30 data. Okay. Another good thing about this Alice method is it has a better control. Of course, we all have this problem in saying, like, what if neural network models are picking some frivolous features, are not deciding factors of classification. This may not generalize to other domains, and it may actually bring a lot of biases to the model. But Alice, the good thing about Alice is because human explanations are included inside of the model. So you have certain constraints in constraining your model's performance. So for example, we look at this particular kind of species called least outcat, a type of bird. And then for the baseline model that doesn't have Alice natural language constraint, so the attention is everywhere. While for Alice, it knows that it needs to concentrate on the head, which is a differentiate part of this particular kind of bird, in order to differentiate with other things. The other one, parakeet, orchid. The same thing goes with particular for the other 2 ones on the right, the Arctic tern and the least tern. So the deciding factor is the yellow bill versus the red bill, the orange legs, and the other one is the red legs. So you have to, so you do see Alice is focusing more on the bill and the legs, while baseline models are focusing on everywhere of the body of the bird. So this also gives you some sort of console that the model is more semantically constrained. It is not picking up a frivolous information that people do not agree with. Any questions before I move on to some other tasks?
Yeah.
Yes, go ahead.
So can you go back to the results table?
Yes.
So is experiments 2, 3, 4, 5, are those 4 rounds of Alice? With
yes.
Those constraints?
Yeah, 4 runs of Alice.
I see. Okay, so those are all pretty big impacts. Great. And then also, can you go back to the slide you were just on? The birds.
This one or?
No. The slide you've gotten to. Yeah. So when Alice is wrong, no. The most recent. Yeah, that one. When Alice is wrong, are does the attention pattern or whatever this your explanation figure here, is it still kind of concentrated but just in the maybe in the wrong places, or does it go back to being diffuse? Like, can you see a different pattern in error cases?
That's a really good question. So what Alice couldn't do well is sometimes certain identifiable feature wasn't present in the image. Then it's having a hard time. It's just like the attention is not concentrated. So there are cases, there is sort of confusing examples that the beak wasn't detected correctly.
So that's cool. You can then use that as a confidence measure, is looking at how much red you get in the concentrated area.
Okay, any questions?
Yes, Joe, I have a question actually. My question is related to the semantic parsing part. So I wanted to ask that, so in that, yeah, if you can go to that slide. Usually for the semantic parsing, have you tried to use the, let's say, if you have a small set of labeled data, have you used the attention of a classifier to see which token it attends more, and then use that token as the most important part of your text, or what you usually do in that step?
Yeah, so here we're not really fusing the language feature with the vision feature. We're just extracting information from the natural language sentence. And then we find the particular parts, the name of the parts, and then we're trying to translate that directly to the visual location of the patch. So there is no sort of attention really going on with the language part.
Oh, I see. So you see based on how much the text, which part of information you can find in the image, and then you extract that part of image.
Yes, that's right.
Oh, I see. Okay, thank you.
Okay.
So, Dr. Yu?
Yeah.
So how did you pick the attention? How do you pick the attention for visualization for this slide?
This is not like a picked attention. It's just the classification model's attention.
Yeah, so I believe there are many layers of the model and many attentions. How do you pick the one that you present here?
I think it's the last layer. You can take a look at the paper for details. We also have code available.
Thank you.
So Alice is not just sort of one task applicable. It could be applied for anything. For example, we have this particular task called social relationship classification, which is I give you an image. I want to ask you what are the relationship between people in this image. So for example, on the left is sports team members. On the right is colleagues. So the same thing would apply. For example, we would ask people, what do you think is the deciding factor that you determine this is a sports team member other than colleagues? And the people would say, oh, the president of football is more like a sports team member, while the president of laptop, books and ties are more like a workspace. So we can use these objects as a particular grounded examples of Alex patches in order to make better classification. So I also wanted to point out Alex is not particularly only designed for image classification, but particularly here we're just using image as an example. You can definitely use it for textual only classification. Then it will come into a lot of similar works, such as Snorkel, which uses natural language and use it to translate into a command and label unlabeled data. But here we are mostly trying to extract information and put it into a classifier. I know Xiang from USC are also doing very similar work. Particularly here, we just, Alice is a particular framework that is applicable for both text and image. It's a very simple idea. You can use it for various tasks. I also wanted to point out, this is just the social relationship classification. You can see it's also like around 20 15 to 20 annotations to per natural language explanation. So we previously were just talking about contrastive explanations between classes. There are definitely all other smart questions you can ask. For example, we can ask questions that constrain the problem holistically. For example, I can ask you how rare this bird, how rare do you usually see in this, do you see this bird in Central Park? Then, for example, we have a data set as a natural tracking of the Central Park. Then we know we should reduce in terms of the weights and of how frequently this bird should fly. Counterfactual examples, for example, we can ask you differentiate dogs and cats. We can ask you, hey, this example looks like a cat, but can you tell me what should I do in order to make it into a dog? Then you can synthesize examples to augment your existing data set. You can also definitely ask hard examples, which is more likely to say, hey, can you give me any hard examples that would really confuse me, so that you can elicit hard examples from the user. So there are definitely different ways you can sort of expand the pipeline to make it more flexible, more effective, and more targeted towards your task. Of course, in terms of algorithm, we're talking about more robust, more control. For example, just like we talked about with John earlier, that certain parts of the bird wasn't present in the image, then just one deciding factor wasn't enough. So what if we ask another, what's the second deciding factor of bird A and bird B? And then we can construct an examples cropping out the most deciding factor, only central on second factor in order to improve the classification results. So this is some ongoing work that we're doing now to improve robustness of classification. Any questions before we move on to more conversational instruction? Okay, so now we're going to talk about some more preliminary work that we are still working on. That is sort of more not using just one turn of natural language explanation, but using multiple rounds of natural language explanation. Okay. How are we doing on time? Let's see. Okay. So we have this particular framework called Alfred. Alfred is a new data set created by AI2 and University of Washington. It's about a sort of navigation situation. You get an instruction and you control the robot to explore the place and perform the task. For example, this is turn left and face the dresser, pick up the alarm clock, so turn left and face the dresser. You'll see this scene. Pick up the alarm clock from the dresser, and you pick up the alarm clock. And then you turn left and look, and then face the lamp. So you're kind of facing the lamp. So previously you're not facing the lamp, now you're facing the lamp. And then you turn the lamp on. And then you go into like now lights off to lights on. So this is the higher level description, and the task in itself is just pick up the alarm clock and turn on the lamp. So the input is all the image, basically the environment and the natural language instruction. And we wanted to basically the output to get the correct, every object into a correct state. For example, the lamp is right now picked up, and the clock is now picked up, and the lamp is turned on. So if one step is wrong, the entire task will fail. For example, instead of turning left to face the lamp, you turn right, and you can't go back. So you will basically break as a robot. So that's why if you look at the leaderboard, the success rate of the task is really low. So we're talking about 0.09 on scene success. Scene is a little bit better, but not that much better, 0.3. So there's a lot of space to improve. And we think natural language conversation could help. So what we basically wanted to do is simple. If you don't know what to do, ask people for help. So this type of a theme of asking robots, asking humans to help robots has been there for a long time. There is Manuel Velasco's work with Colbat asking people to clarify reference expressions. For example, if people say go to the department's office, and then you want to know who is the department chair, and then the robot can ask people to clarify that, and you will log that into the database. So Ramuni from UT Austin has also done a fair amount of work. How Domain has a recent navigation data set, Nancy on similar form. But here we just mostly wanted to see in this kind of virtual environment that has a lot of actions, a diverse set of actions, what can we do? So here we just say, if we have an ambiguity in terms of not sure what to do, we can always ask, should I turn left? And then people can respond to you, no, you should turn right. And then you will avoid making such mistake. So there are different scenarios we would encounter. So if we are only confused about the action of the robot, we can just simply ask the action. Well, if we're not really sure about the objects, then it's a little bit harder. For example, where is the clock? The robot is confused, couldn't find the clock. And the human said, can you find a bed? And the robot said, yes. Then clock is the object on the far right of the bed. So basically you have to find another object and then use reference expression to locate the clock, which is a little bit harder. So if you look at some statistics of the baseline, you see the accuracy. So because this task has two subtasks. First, you have to provide the right action for the robot, and you have to provide the correct mask, which is the correct object that you're gonna impose your actions on. So usually the object detection wasn't that hard, but the correct actions are usually the bottleneck. So how can we make sure that we improve on the correct action? So of course, the other problem is we can't always ask questions and not move. It will basically utilize all the human resource, and the human wouldn't be happy to help the robot. So it's always a trade-off between the task sets and how many human resources you're going to use. So there is also an optimization there. The baseline framework for this task is very simple. You have the language part of the instruction. You feed it an LSTM or a transformer or whatever. And you have the image of the sequence of the image of the task. You can put it in a ResNet in a supervised way. And then you have a representation you can combine. And then finally, you want to do two types of prediction. First is what is the action? For example, here is pickup. And the second is the mask of the object, which is the clock. So you wanted to improve on the last thing is basically how do you put the action and the objects to a better accuracy. So the action, so the baseline, of course, is you just only do R mass in terms of your actions. You have a list, so you just pick the one that has highest probability. Well, for us, we can have, if this highest probability is below a certain threshold, we're gonna request human help. Otherwise, we're just gonna, if it's above the threshold, we're just gonna do the action. Then another thing we talked about is what about the object? What if we can't find the object? That is more complicated. First of all, we need to parse the sentence to find the unigram, not even parsing, we're just tokenizing it. You find the unigram, bigram, trigram of the sentence. And then so you detect what are the possible combinations of objects. For example, alarm, desk, and so on. For each detected object, we want to look at, is this the highest, so look at the threshold or likelihood of which object that we're referring to. And if it's below certain threshold, we ask questions to get more referential expression. Otherwise, we're gonna just pick that particular object. For example, I can't find the object. It is a clock. If a clock is detected based on the image classifier, then we end the task. Otherwise, we couldn't find the clock. And then we say, I can't find the clock. And the human say, could you find a desk? And the robot say, yes. So now at least the object detector for desk was working. And then we ask, then the human would say, then the clock is the far right object on the desk. So once you locate the desk and you see there are a couple of objects, And then the object that detected on the rightmost is going to be your clock. The experiment setup is pretty simple. 80% train, 20% of original train as validation. And the test set is original validation set because it's a leaderboard task. You don't get the testing set. So one of the biggest questions for us is because this data set wasn't set up for our setting in terms of there's no natural language questions for it. So we basically generated all these kind of questions ourselves. And then at the same time, looking at the environment, we get the ground truth to generate the answer. What we can do currently, we're still improving our results. So without the action question answering, so we have two types of things, right? We ask about action and we ask about the object reference. If we don't do the question answering on the action, so we decrease a little bit in terms of the unseen environment. But if we don't do reference expression on objects, we decrease a lot. For the seen environment, it's the same idea. The objects are really difficult to get. And here we're testing on the condition that the question you ask per task is about 1.7. So we're still improving the results, but the idea is simple that how can we use natural language conversation in order to improve these kind of robotics tasks. Okay, any questions on the task? Okay. Cool. I can also, if we have a little bit of time, I can show you some of the demos that we have in our lab that is not about this particular project, but in dialogues in general.
Bonsai, so he came with that.
So this is a recording of my student, Michelle, talking to our Amazon Alexa social bot. So we won the Alexa social bot in 2018, and we have been working on this a little bit more. This is Michelle talking about pets.
Dog is named.
Come on.
Our dog is named Bonsai, so he came with that name. We think it fits him pretty well.
That is a great name for a dog.
Yeah, he's kind of short, like a bonsai tree, so it works.
Tell me, how long have you had bonsai?
We've had him for a little over a year now, yeah.
Aw, you must be great friends.
Yeah, we are.
Yeah, for that one, we're doing long-term memories and we're doing some affects. So another one here is about tutoring on second language learning for communication skills. So this particular user is interacting with our system that is pretending to be an interviewer, and this user is an interviewee. So you can practice your interview skills and your second language communication skills through this. And we are doing some adaptation based on user satisfaction, sort of lack of engagement or uncertainty in order to improve the system's engagement. Can you see?
What would you do if you had a disagreement with a coworker? Would you prefer to settle the matter directly with your coworker, or would you report the incident to your manager?
I'd talk to the coworker so he knows what he's doing and he doesn't get in real trouble. Well, maybe if he does something really, really bad, then maybe yes, I'll report him to the manager.
And what do you think the manager would do next?
Cut his pay a little bit.
So we detected sort of disengagement here, averted gaze, or answer
I
voice.
don't really know, actually.
Yes, I think a lot of managers would do that.
And then we give him an encouragement so he could stay in the conversation for longer. In the end of the conversation, we'll give him feedbacks about his grammar problems, variety of vocabulary, syntax structures, and so on. Okay, I think that's everything I want to cover today. Any more questions?
Can I ask you questions about the two demos you just showed?
Yeah, of course.
So in the first one, I noticed that your student was very engaged with the bot. We've seen that a lot of times users, when they're talking with bots, are not so willing to talk. Did you find, I mean, when you put these things out in the wild, are you able to get more longer engagement? And if so, what's your general strategy for encouraging people to talk a while?
Yeah, that's a good question. A lot of people come with different intents. Some of them just want to test the ability of the system. Some of them just came in with a vicious intent of trying to destroy the chatbot. Some of them accidentally triggered it. So it was different intent. They have very different behaviors. And it was different, like a demographic, like kids versus adults, adults versus lonely adults. They're all very different. So we tried a lot in terms, for example, positive affects, have a bank of rich topics, giving them immediate feedback, remember their previous conversation. All these would contribute.
The second one, I noticed, right, there were pauses between some of the parts of what the human was saying. So do you have a good strategy for knowing when the actual turn is over to prevent?
Yeah, that's a really good question. So this particular thing was not on Alexa. Alexa has its own endpoint detecting that we can't change. But in different scenarios, for example, these kind of interview settings, you wanted to engage people, wanting them to contribute more. So that's why we have a sort of a more laid back endpoint detecting here.
Great, thanks.
Hello. Can I have a question?
Yeah.
Yeah. Nice to see you, Professor Zhou. My question is actually about the reliability of the whole system. So when, for example, in the video that you showed earlier, that the conversation seems to go very smoothly. But I'm curious, so in your kind of whole experiment running and then also your experience, how reliable is the whole system that the response or the question actually were kind of on the right topic and was went smoothly? Yeah, so that's my question.
Yeah, so there's definitely a lot of cases that our systems will fail. And there's, of course, certain system bugs will crash the entire system. And we do have a lot of fallback in terms of like, oh, we lost I lost my train of thoughts. Can you remind me again? Or if there's ASR errors, or if it's like a missing tokens, we have various strategies to recover. Of course, there is, for example, the ASR, when we got the ASR and it's always empty and there's nothing to understand, then we'll try to change topics or ask easier questions. For example, WH question, open questions are much harder to respond than yes or no question. So you can always try to adjust the system in order to tailor to user with different responses.
Okay, thank you. Yeah, that's my question.
So first of all, if I also may say, thanks so much, Joe, for the great talk. And do we have any other questions from the audience? I'm also looking through the chat and we don't have any questions there. Okay, great. Oh, I think it's, okay. I just a question came through chat, sorry.
Oh, I saw them. What the done through Python? So are you talking about the explanation work, or are you talking about the chatbot work? Alice, okay. Yes, it's through PyTorch.
Okay. Okay, so I think if there are no other questions, then we can all again thank Zhou for the great talk, and we can give her a little break before the one-on-ones starting at 12:30.
Thanks so much for inviting me. Do contact me if you're interested in working together. Bye.